So I want to step sideways for a moment here and consider the insight that we can gain by considering not the Lagrangian form of momentum conservation and how that develops into Euler's equation, but to consider the conservation of momentum from an Eulerian perspective, where we want to consider the Eulerian rate of change of momentum density. So I'll show you what I mean by that, and we'll see what we can learn by looking at it this way. So all of this is aimed at being able to tell us a little bit about RamPressure. And RamPressure is an important concept in astrophysics. So I want to develop it up. So here what we're going to do is we're going to consider instead, consider instead Eulerian rate of change of momentum density. And so that's partial derivative with respect to time of rho u, instead of considering rho times the partial derivative of u. So here we're going to look at the component notation of a summation convention, where we're going to deal with a series of components. So let me just sketch this out for us here. So what we want to think about is consider a volume and this volume has a series of repeated indices. And those indices are that we have the j direction here, and we have the I direction there, and we have a flow in the j direction that might go like that. So now we want to think about the Eulerian equation. So we're going to consider the partial derivative with respect to time of rho u, and that is the mass per unit time hitting the surface S in the j direction, if we're considering it with respect to an I component. So in fact, better to write it this way, to write it in terms of I, and that is equal to rho times the partial derivative of ui with respect to time. This is just a standard partial derivative equation. Ui, the partial derivative of rho with respect to time. So this is over the I component. So this is the mass per time hitting the surface S in the jth coordinate. And we can consider how to write out this portion. That would be equal to minus rho ui, the partial derivative of the jth coordinate ui dxj. And this can be done for a number of different coordinates, dj, dxj, Kronecker pressure times Kronecker delta, dij, plus rho gi. So all of that portion of the equation is just the momentum equation. And then this second portion here is just going to be the conservation, the continuity equation, the mass conservation equation. So that is equal to ui partial derivative with respect to xj of rho uj. And all of that is just my same d dt rho ui. So from there, I can rewrite that as the partial derivative with respect to time of rho ui is equal to minus the partial derivative of dxj of rho uj ui plus the pressure times the Kronecker delta plus rho gi. And the first one of these terms here is what's defined as a stress tensor due to bulk flow. And this part is the diagonal of the stress tensor due to random motions. So we know that the force on the I surface, or on the J surface from the terms in the I direction, is equal to the stress tensor times the surface. So the total stress tensor is the sum. All of this is the stress tensor. And the stress diagonal of the stress tensor is just the pressure times the Kronecker delta. So we can rewrite again our equation with respect to time. Rho ui is just equal to the partial derivative of ij plus rho gi. Stress tensor ij is equal to rho uj ui. I'm just writing the same thing in different ways so that you can see where it all comes from, times the pressure times the Kronecker delta. And that relates to the force. A stress tensor is the force in the direction I acting on a surface with normal along J. So keep that in mind. It's the force in the direction I. So let's say I is this way, acting on the normal of a surface which has on a surface which is normal along J. All right, so where can we go from there? Well, we can think about what these different terms mean. So the first of those terms is that the isotropic pressure. So the isotropic pressure gives a stress tensor that looks just like P delta ij, Kronecker delta ij. So that's saying that it's in all directions equally. They have a pressure of a particular magnitude, and that produces pressure in all directions equally. Now, the flip side of that is that you could have an additional term on my, so this one is the isotropic pressure. The additional term is pressure due to flows. And that's what's called the RamPressure. So the RamPressure just writing this out for us to have here. And the force in the I direction is the stress tensor. in this direction. So thermal pressure is independent of I and J. It's a scalar. And it acts perpendicular to any surface. So imagine the following scenario. Imagine that we have a pipe, and in that pipe there is gas that is warm with a pressure P, and it has a flow U in that direction, and we have defined our coordinates such that this is the Z coordinate, the Y coordinate, and the X coordinate. So we have isotropic pressure from hot fluid. That means it's pressuring in every direction. So all sides of the pipe feel the pressure. But the gas is flowing only in my Y direction. And so it's only producing any additional pressure on the surface that is at the end of that pipe. So that is what's called the ram pressure. So the ram pressure depends on I and J for bulk motions, and it gives a 3x3 matrix of elements rho, ui, uj, where the stress tensor looks like the pressure, 0, 0, 0, pressure plus rho u squared. This is my pressure of my pipe with the hot fluid. And this particular term, the rho u squared, is what's defined as the ram pressure term. So let me show you an example of that. So the example that I want to bring up here is the example shown on the screen. So these are galaxies from the survey by Chung et al. And you can take for example, NGC 4522. The galaxy is moving in this direction. So it has a velocity in that direction, and it therefore feels a ram pressure force, or feels ram pressure due to that movement there, and it sweeps the gas back behind the galaxy in a curved pattern. So the ram pressure in the galaxy passing through the intercluster medium example here is the density of the intercluster medium times the relative velocity, that is the velocity of that galaxy with respect to the stationary intercluster medium, squared. And this is a very simple equation that allows us to calculate how much ram pressure a galaxy may feel due to its motion through an intercluster medium. And that ram pressure has to be balanced by something. Otherwise, a galaxy would lose all of its gas. So in this case, it could be balanced by the pressure exerted by the gravitational force. And that's what could hold the gas in. And that can be related out. And this was done by Gunn and Gott in 1972. They said that if the ram pressure is greater than 2 pi times gravitational force times the surface density of stars with respect to radius times the surface density of gas with respect to radius, then the galaxy will lose some of its gas due to a RamPressure effect. And it's a fairly important effect, and we'll develop it a little bit more in some of our tutorial activities. So I'll stop there, and we'll pick up again next time on Poisson's equation.